Welcome back, everybody. So for a while now, we've been building up our toolbox of integration techniques, and I'm in 7.5. In this section, we're going to put them all together and just tackle a whole bunch of different integrals. And so today in this video, I want to real quick just talk through the top of our worksheet here, reminding ourselves of the different integration techniques that we've seen so far, and then we'll go ahead and I'll talk through solutions to our first three of the integrals on the worksheet. So you can watch those if you'd like. All right, so before we even started chapter 7, all right, we had these two basic techniques. One is we could just algebraically, change the way our function looks, split up a fraction, do stuff like that. Let's make it look different. And we had u sub, which undoes the chain rule, right? And thinking about the chain rule, the idea is u sub is probably going to be helpful if we have an inside function somewhere, and also the derivative of that inside function is more or less floating around, right? It could be off by a constant multiple or something like that. But those are the two basic things to look for. Our next integration technique that we saw, the first one in chapter 7, was integration by parts. And this is where we undid the product rule. And the idea is that we have integration by parts as a possibly useful technique if one piece of our function we'd like to replace it with its derivative, and the other piece it would be helpful to switch out with its antiderivative. Right, that's exactly what integration by parts does, and so that's what we're on the lookout for. Next, we saw how we could handle integrals involving trig stuff, specifically products of sines and cosines, and even secants and tangents we can handle. We have our strategies there. We looked at the trig sub technique, which is if we have one of these basic forms or something close to it, we can inject trig into our function in order to use one of our Pythagorean theorem identities and collect things. And then last but not least, we have our partial fractions strategy, which is designed to take a rational function and break it up as a sum of simpler pieces, right? And we can do this if we have a bigger degree in the denominator. Right, and so these are kind of what to keep in mind and some things that we're looking at that suggest one strategy or the other. We also, as we're working through these, don't want to forget about just antiderivatives that we know. For example, these integrals here, right? These antiderivatives we know just outright. The first one being inverse tangent, this next one inverse sine, right? So we want to keep those known formulas on hand as well. All right. And so with that, let's start in with these first three integrals. And so if you haven't yet spent time working through these, pause the video and spend some time getting to know these integrals, trying some things out, and seeing how far you can get with them. All right, well, let's start talking about these. So this first integral, what stands out to me right off the bat is, first of all, it is an integral involving a rational function. All right, we got polynomial up top and a polynomial in the bottom. A little issue is that, if we're thinking partial fractions, the degree up top is not less than the degree in the bottom, so we'd have to do polynomial division to start. An important question too, if we're thinking about partial fractions, is looking at this denominator. It'd be nice if we could factor this, and we can hope for the best and try and find two numbers that multiply to be -8, add to be -2, and indeed these numbers do exist, -4 and +2, and so this actually does factor nicely. Right, even if it didn't factor, it wouldn't be the end of the world, but it would be definitely a lot more difficult. And so these two pieces together definitely suggest partial fractions for this first one. So let's see how that looks. So here are the notes that we've been talking about so far. We do need to use polynomial division to start because the degree up top is equal to or greater than our denominator's degree. It does factor nicely, which makes us happy. But here we go. To use polynomial division, we put the numerator inside the house, what we're dividing by outside. And looking at the leading terms here, 3x squared inside the house and x squared outside, we just ask, well, hey, what do we need to multiply that x squared to match up here? And in this case, it's 3. Right, and multiplying that through, and then subtracting, we end up with polynomial 6x plus 22, and this right here is our remainder. Right, the degree of this polynomial 1 is less than the degree that we're dividing by 2, and so this is our remainder that we can work with. And so using our polynomial division work, right, we know that our original rational function here equals that quotient 3 from the top plus our remainder divided by what we were dividing by originally, right? And now the idea is, since we've done this division and this degree is small enough, we can now use partial fractions on what's left here. And using the fact that our denominator factors in these two linear factors, right, partial fraction says that we can associate to each one of these linear factors a term. Right, so to x minus 4, we get the a over x minus 4, and the x plus 2 gets the b over x plus 2. Right, just these constants because these factors are linear, they're degree 1. Right, if one of these was a irreducible quadratic, we'd have to allow for a linear up top, some bx plus c or something like that. All right, I'm going to slide down and we'll just look at the right-hand side of the page here, working through and finding now these unknowns a and b. All right, same process as we've seen before. We just clear out the denominators by multiplying both sides by the denominator of our original function here, x minus 4 times x plus 2. Right on the left-hand side, the denominators will just disappear outright. And on the right-hand side, these will distribute to both these terms. Each one, something different cancels out with the denominator. And what we're left with is what we see here, ax plus 2 plus b x minus 4. And at this point, we want to go ahead and plug in some various x's to get equations that just involve numbers and our unknowns a and b, and figure out what those are. All right, and some nice x's to plug in come from looking at our linear factors here. Looking to kill those off, we can plug in -2 and +4. And if we carefully plug in x equals -2 wherever we see an x in our equation, we can boil things down and see what our coefficient b is, 5/3. Right, just simplifying that fraction, -10/6. And then similarly, if we plug in 4 wherever we see these x's, we can then get 46 equals 6a, divide by 6, and simplify. So 23/3 is what a equals. And it's totally fine that, right, these aren't integers. That can very well happen. So as long as we've done our work correctly, then these a and b coefficients are just kind of whatever they end up being. So anyways, we now know, right, our a, what goes on top of the x -4, and our b, what goes on top of the x + 2. And so now we can go ahead and actually compute our integral. Right, using our polynomial division, we saw that this equals 3 plus this fraction over here, getting to be a lot of colors, this fraction. And that we broke up using partial fractions. And here's our a, and here's our b substituted in. Right, and we can just slide those out in front of both of those terms, and each one of these terms we can integrate. Right, since these are just linear in the denominator here, those antiderivatives are just going to be natural log of absolute value of those things. And so integrating each one of those pieces and adding our plus c, those are our antiderivatives. All right, well, with this second integral, again, if you haven't worked through this one yet, take some time and see what you can do with it. But let's talk about it. Here, what stands out to me is we have this trig function, sine of x, and right next to it, multiplied on an x squared. And so right away with this product, I'm already thinking, you know, maybe integration by parts. Let's think about kind of when that's useful. We want to have a piece that would be helpful to replace with its derivative, and another piece to replace with its antiderivative. And here, the x squared is kind of what's going to be nice to replace with its derivative. That's because the exponent drops, right? Sine, differentiate, or anti-differentiate, not going to change too much. We'll have some trig function. And so with that in mind, let's see where we can get with integration by parts. And so working this through, right, we've chosen our u, and that also chooses by default our b prime, and integrating and anti-differentiating fills in the rest of the grid. And now over here we can just use our integration by parts formula, uv minus the integral of u prime v. And putting those pieces where they go, here's what we're left with. And at this point, we can just do a little simplifying here. Take this negative, pull it out front, and over on the right, we had a constant multiple of 2 and this -1. Let's pull those out. The negative will make this negative a positive, and we'll have a 2 out there. Now with dust settling after our first integration by parts, we're looking at this integral here. And this is not an integral that we know an antiderivative for right away, but Once again, we have a product, and thinking about this x here, well, if we could replace that with its derivative, life would be good. And so this is another integration by parts to get the rest of the way here. So here now, our u is that x, and so our v prime is the other stuff. Differentiating and anti-differentiating fills in the grid, and we can now fill that in over here. What do we end up with? All right, our formula is uv minus the integral of u prime v. Right, and this is all of this is being multiplied by our constant multiple of 2. So here I've used giant parentheses to show that. And feeding everything in where it goes, we're left with just the integral of sine, which we know is negative cosine and so I think I have a typo here. Let me think through this real quick. Yeah, it should be negative cosine for the integral of sine. Because the derivative of negative cosine would be negative negative sine, or sine. And now, so that negative is going to, if we pull it out, it's going to make this a positive. And so I'm thinking that this should be a positive here. All right, so here I have taken this 2 and distributed it in. Yeah, let's go with that. I'll make a note if, or someone call me out on if I made a mistake somewhere with the sign, but I think that should be a plus 2 cosine x at the end. All right, last but not least, integral of 3x squared minus 2 over x cubed minus 2x minus 8. Again, if you haven't worked through this one yet, take some time and see what you can make of it. But let's start talking about it here. So again, kind of similar to the first one, right? Here, what stands out to me initially is that we do indeed have a rational function going on. The degree of the numerator is less than the degree of the denominator, but the degree of the denominator is 3. And that's not something that we know how to associate terms to, right? For partial fractions, we want to factor everything into linear and irreducible quadratic terms, or quadratic factors. And so, if we're trying to think that way, then to factor this, we're really looking for a root of our cubic polynomial here, x cubed minus 2x minus 8. And if we're curious about how this might factor, we could bring up a graph. And so here is our cubic polynomial. And so it does have a root, and so it would factor, but where is the root? It's at like, not at something nice. It's like in between 2 and 3, 2.331-ish. And so it's not going to be some nice clean factorization. This is going to be some irrational number, and it's going to be weird. And so with that, thinking about factoring this, it's possible, but it's not going to be so nice. And so partial fractions, say at this point, hopefully not. And so, well, if not partial fractions, well, what else? What else could we possibly try? This doesn't look like anything we want to inject trig into. It doesn't have sines and cosines already. It doesn't really look like a integration by parts sort of product, or even if we could try and force it, it'd be pretty awkward. Nothing at least too obvious that we could do to algebraically mess with this. We could potentially split up this fraction as two fractions where the first numerator is just this first piece, and then we have minus and then 2 over our denominator, right? We could break this up as two fractions, but not so clear what to do from there. And so really this integral is meant to help us remember that we still have our basics. Right? We still haven't touched on u sub. And in fact, right, thinking about u sub, the only thing kind of real natural to think about is, well, what happens if we let the entire denominator be our u? Well, what's the derivative? 3x squared minus 2. It's floating right up top. And so u sub is definitely going to be the way to go for this one. And if we let our u be our denominator, our du is right there. And so doing our substitution, the 3x squared minus 2 dx, that just becomes our du. And then our whole denominator just gets replaced with u. And we're left with exactly, the derivative of natural log absolute value of u. And so we can integrate, replace our u, and we're good to go. So we definitely don't want to forget about u sub, even as we are thinking about these more involved integration techniques as well. Well, that's it for today. If you have any questions, post those to Piazza. Good work, everybody, and I'll see you next time.